So no talk about approximation algorithms would be complete without a discussion about the knapsack problem. So we've been comparing and contrasting knapsack and TSP all the way through the semester. So let's not stop now. Okay, so let's go back to the knapsack problem that has indivisible items. So this is the 0-1 knapsack problem. We can either take an item or not take an item. We can't take parts of an item. And let's look for an approximation algorithm for this. So here's the question. Can we find an approximation algorithm for 0-1 knapsack? Okay, so let's think about how we could do this. Now we've already looked at two greedy algorithms for this, so let's actually compare them a little bit and see if either one is an approximation algorithm, is an approximation algorithm for any approximation factor. So let's just draw kind of a cartoon instance here. So we've got 0, 1, 2, and so on. Each one of these items has a value. Each one of these items has a weight, 0, 1, 2, and then each of them has a density, right? Each of them has a value divided by weight. And so we've seen a greedy algorithm that sorts based on values, and so we're going to call that greedy 1. So this is the one you did in your homework at the beginning of the semester. So greedy 1 sorts on value. Okay, well, let's call it greedy 2, the one that sorts on density. Okay, we've looked at both of these. The greedy 2 algorithm is the one that is optimal when we have divisible goods, right? So when we have the fractional knapsack problem. And we've already seen that greedy 1 is not optimal for the 0-1 knapsack problem. Okay, so let's take a look at these and see what we can learn about their approximation factors. And by the way, I'm not going to do greedy 1 here. So you've already studied greedy 1 in an early homework, and then on your last homework, you're going to prove that greedy 1 has an unbounded approximation factor, right? Greedy 1 is not a C approximation for the knapsack problem for any finite C. Okay, so here's our sort of fact 1. We'll leave those there. So fact 1, you'll prove this in your homework. Greedy 1 is not a C approximation for any C. For any C, any finite C. Okay, in other words, it has an unbounded approximation ratio. Okay, and so you'll work on this in the homework, and you'll use the same concepts that I use to show fact 2. So fact 2 is very similar. In fact, I'm just going to copy fact 1 and then change the wording just a little bit. So fact 2 goes in here. Fact 2 says the following. Greedy 2 is not a C approximation for any C, for any finite C. Okay, so we're just following our theme of greedy is not working out well for us on the knapsack problem, or so it would appear. Right. So let's think about why this is the case. So let's prove this one. Okay. So here's the way to think about this. Right. The way to think about proving that an algorithm is not an approximation algorithm, is not a constant factor approximation. With these, the greedy algorithms, they see a list of items and they sort along a particular axis, and then they say, I'm going to just walk down that list and sort it in this particular way, and take things until I can't take things anymore. So what I need to do is I need to think about tricking that particular greedy algorithm into putting the items in the wrong order. Or alternatively, I have to think about tricking that greedy algorithm into filling up all the space within the knapsack before they get to the stuff that I actually want them to take, right? That they should be taking. So how can I trick this algorithm into taking the wrong stuff? Well, what is the greedy 2 algorithm doing? So the greedy 2 algorithm is sorting on this axis, right, on that column. So what I need to do, and the heuristic that the greedy 2 algorithm is using is it's saying, high density stuff packs a lot in, per pound. So let me start with that, right? So in order to trick the greedy 2 algorithm into taking too much of the wrong stuff, I have to choose my values and weights so that there's high density stuff that wastes enough space that I can't fit in some high value stuff. Okay, so let's work this thing out. So here's the picture that I'm going to draw, and this is going to be kind of the family of examples that show that the greedy 2 algorithm is not an approximation algorithm for any constant factor approximation. So I'm going to let my weight be W, my capacity be W, and I'm going to think about my knapsack as looking like this. Okay, so I'm just going to give 2 items, right? I'm going to say there's exactly 2 items here. So my items are going to have, I'll have my values, I'll have my, let me scoot this over just a little bit. I have my values, I have my weights, and then I'll just compute the density ratio here, so VI over WI. So the first item, I'm going to think of as the item that should be in the box. Okay, so this item has a value of 9, right? And I'm picking whatever numbers I want, and I just want to pick these numbers in such a way that the greedy algorithm doesn't take this item. Okay, so this item is going to have a value of 9. So I have now in my mind the best thing that we can do is a value of 9. And so I'm going to trick the greedy algorithm into taking the other thing. And so I want to make sure that when it takes the other thing, now this item can't fit. Okay, so to ensure that this item can't fit, once the other thing is taken, I'm going to make this thing's weight 10. Okay, and it just happened. I mean, I could have picked anything for that 9, but 9 ends up making the numbers work out really well in just a second here. So now what's my value per weight ratio? What's my density? Well, it's 0.9, right? I get $9 for every 10 pounds that I put in, or 90 cents on the pound. So all I have to do now to force my greedy algorithm to pick the wrong thing is make sure that the other thing has a density higher than this. Right? So I want the other thing, let's just say, to have a density of 1. Right? And so I'm choosing that density so that my algorithm picks this thing. And I just need to now make sure that even though it has a density of 1, it has a very small value. Okay, so let's think about what the value could be. Well, it could just be 1, right? I mean, if the value is 1, that's much, much less than 9. And there's no reason I can't, create a weight also to make the density equal to 1. Okay, so here's the idea. This thing gets picked by the algorithm, right, because it has the highest density by greedy 2, right? So this thing goes in here. And then once it's in here, this thing doesn't fit, right? So this can't fit. And so there we go, right? So what's the approximation factor on this instance? Well, the approximation factor is going to be 9, right? Where what we have is the optimal, right? The optimal here would take. Right, the optimal would take the first item with a value of 9. So the optimal is a value of 9, but greedy 2, greedy 2 gives us a value of 1. And so then we could ask, could I change these numbers so that this is even worse? And of course, right? So with these particular numbers, my approximation ratio is 9 divided by 1. And so I can make this as big as I want if I make the denominator small. And how do I make the denominator small? Well, I say rather than a value of 1 and a weight of 1, let's make a value of epsilon and a weight of epsilon, right? So I can go in here and I can say, well, there's nothing about this that required me to have, integer numbers in here. So let me just make this some tiny, tiny little sliver. And then the greedy algorithm picks it, wastes all the room, and we can't fit the right thing in, and we end up with a 9 over epsilon now. a 9 over epsilon approximation ratio, and as epsilon goes to 0, oops, not to infinity, as epsilon goes to 0, this thing goes to infinity, right? So the approximation ratio is unbounded. So this analysis proves that greedy 2 is not an approximation algorithm, or does not have a constant factor approximation, or is not a constant factor approximation for the knapsack problem. So is not C-approx for knapsack. So now let me illustrate for you an interesting fact. The greedy this is a worst case family of instances, right? The instances parameterized by that epsilon. So worst case family of instances for the greedy 2. What happens if I run greedy 1 on this? So remember, what does greedy 1 do? Well, greedy 1 sorts by the values and then walks down the list. Well, greedy 1 always gives the optimal answer here. Okay, so on an instance that is a worst case instance or a worst case family of instances for greedy 2, greedy 1 is optimal. Okay, so there's our observation. Greedy 1 that sorts by value is optimal, returns the optimal answer on this instance. And so on your homework, by the way, this is an aside, but on your homework, when you prove that greedy 1 is not an approximation factor, on the instances you design to trick greedy 1, you should try to see what happens if you run greedy 2 on those instances. And in many cases, you're going to find that greedy 2 is optimal for those instances. Okay, so what do we do with this? Right? What do we do with this weird dichotomy where on an instance that's worst case for one, it's optimal for the other? Well, let's just run both, right? There's no reason you can't just run both algorithms on a problem instance and then just return the higher value. So it turns out that if you do that, that is a 2 approximation for the knapsack problem. Okay, so here's our fact. Greedy 1, let me write it this way. It is a 2 approximation. To run greedy 1, greedy 2, and return the best solution found. Okay, and I can think through the proof of that for you in person if you'd like. I'm not gonna record one on the video, and you can find the proof of this in various places. But this is one of the fun kind of results that you find with knapsack, is that either of these two algorithms by themselves is terrible, but if you put them together, it turns out that what's bad for this one is solved well by this one, and what's bad for this one is solved well by this one. And another kind of like low-hanging fruit kind of a result. You just do the two obvious things and see which one's better, and you've got a good answer. Not obvious up front, but turns out to be provable.